If you were to ask a physicist, what is the most important mathematical tool that he or she has, the answer that you'll probably get is differential equations. Indeed, without differential equations, we wouldn't be able to understand so much of the world around us. We couldn't understand how planets move in orbit around the sun. We wouldn't be able to understand how electricity flows in circuits with capacitors and inductors, and so much else. But what is a differential equation? Very simply, if you have an equation, left side is equal to the right side, and if one of those sides contains a first derivative or a second derivative or the third derivative of a function, etc., then that is a differential equation. In this lecture, we'll deal with the simplest kinds of differential equations in which there is only one first-order derivative. There are many physical situations where that's important, and so let's begin by looking at some. But before we get into differential equations and where they come from, I want to tell you the difference between a differential equation and an ordinary equation. An ordinary equation is something like this. Let's say x plus 3 is equal to 7, which means that the solution is x equals 4. Or you could have something like this, x squared minus 3x is equal to minus 2, in which case you would have two possible values of x, 1 or 2. Of course, it could be very complicated. You could have tan x equals square root of x squared minus 1, and then you'd have to do this on the computer numerically or whatever, and you'd get x equals this value and this value and this value. But a differential equation is different from all of these. A differential equation is of the form dy by dx equals some given function of x and y. Now, this is a first-order differential equation, meaning there is only dy by dx. There is no d2y by dx squared or any higher derivative. That's why it's called first order. The function f of xy could be of many, many different forms. If you're lucky, f of xy equals 0, then you know how to solve this. Any constant value of y will satisfy this. But in general, it could be anything. It could be, just to give you some examples, it could be 3x squared plus 1, or f of xy could involve y, just plain y, to some power, let's say. Or it could be something very complicated. F of xy is, let's say, 1 over square root of 1 minus sine of y times e to the x plus square root of x. Now, this sort of a given function f will probably result in an equation that you cannot solve. In fact, most differential equations, even first-order differential equations of this kind, cannot be solved in general, but there are a lot of equations that we will be able to solve. But what is it that we have to solve for? What we want is y. This is our unknown, and it is a function of x. So, this is an equation which says differentiate y with respect to x and get back this given function f of xy. So it is not your job to find out what f of xy is. Your job, or the job of anyone who is out to solve this differential equation, is to find y of x. Now that means you've got to find y of x for many, many, many different values of x. So this requires knowing the function, knowing y of x, in other words, at an infinite number of points. Because, of course, x is a continuous variable. And that's really the difference between solving an equation like this over here, let's say, and solving this equation here. Why should we be interested in differential equations anyway? Let me give you a number of physical situations where they might arise. So, as our first example, let's take fish in a tank, and let's call n of t as the number of fish at any time t. We are interested in knowing how this number changes with time, that is to say, the rate of growth of the population of fish. And as a hypothesis, we could say dn by dt is proportional to n. So the more fish there are, the greater the rate of growth of n. We could convert this into an equality. dn by dt is some constant c times n. The bigger the value of c, the greater the value of dn by dt will be. And now as n keeps increasing, dn by dt keeps increasing. But that means that n will go to infinity, and we've never seen an infinite number of fish in a pond. So therefore, a better equation might be this constant, some constant, times another constant, n0. We'll have to determine what k and n0 are empirically, that is from experiment. And I'm going to now hypothesize this equation. You see that dn by dt will increase as n increases, but then when n comes close to n0, then dn by dt will go to 0, and so the number of fish will level off. We have to start with some value of the number of fish at time t equal to 0. Let's call that n0. So then this is an equation with an initial condition, the initial condition telling you how many fish there are at time t equals 0 or any fixed time. So that's an example of a differential equation. Let's take another example. Here is a man who has just jumped off an aeroplane. There is the force of gravity, which is obviously moving him downwards. But as he falls, and falls faster and faster, there is more and more air resistance. And so there's an opposite force, opposite to that of gravity, and that's therefore coming with a negative sign. And let's say that it's some constant times v, or perhaps v squared, or perhaps v cubed. This is something that has to be determined. But let's assume that the force then is mg minus kv squared, in which case Newton's law says that m dv by dt, so mass into acceleration, is equal to the net force acting upon the body, and that from above is mg minus kv squared. And let this v of 0 be the velocity with which he had jumped off. We could take this to be v naught, some number, maybe it's equal to 0. And in that case, what we have is a differential equation in the variable t, and v is what we have to find with this initial condition. But now let me give you a slightly more difficult example. So here's a plane that's flying with constant thrust F. So F is the force with which the engine is pushing this plane forward. There is air resistance, and let's say that as before it is kv squared. So this is the net force that is acting upon the plane as it flies horizontally. But now it's also burning up fuel. And so when we write Newton's law, it will be mass as a function of time. This mass is decreasing with time, times the acceleration. So mass into acceleration is equal to the force, F minus kv squared. And now from here we get dv by dt is f over m of t minus kv squared over m of t. And let's say that this m of t is equal to the mass that was there originally minus alpha t. So alpha is the rate at which it is burning up fuel. So now we have a situation where the velocity is changing with time. F is a constant, but m is changing with time. And this could be an example of how the mass is changing with time. Now this equation, together with the initial condition that the velocity at some time t0 was something, let's call that v0, would then give you an example of a differential equation that has to be solved, and one that is fairly hard. Not all differential equations can be solved exactly or analytically, but you can always solve a differential equation on a computer or a calculator numerically, approximately. To be more precise, we are asked to solve this differential equation, first order differential equation. Dy by dx is some function of x and y, some given function of x and y. The other information we're given is that y has the value y0 when x is equal to x0. Now this is not a simple thing, because you need to know y everywhere as a function of x in order to be able to take the derivative, and then if you take that derivative, that's got to equal to this. Well, let's assume that we do know y as a function of x. So that's this curve over here, which is the solution that we are looking for. So that's this curve over here. Now, let's take the starting point to be x0, y0. We do have a starting point because when x is equal to x0, we are told that y is equal to y0. Otherwise, we cannot solve this numerically. Now let's go to another point, which is x1, y1. And this distance delta x is x1 minus x0. And then we can go to another point, which is close to it, x2, y2. And then another point, x3, y3. And for simplicity, we'll assume that by going delta x each time we go to the next point and then the next point and so forth. Now, let's approximate dy by dx by saying it is y1 minus y0 divided by x1 minus x0. And that's equal to the value of f somewhere in between them. But since we know it only at this value over here, we're going to write this as f at x0, y0. Now this here is known by hypothesis because we know what f as a function of x and y is. And so this right-hand side is known, in which case we get y1 is equal to y0 plus delta x, f of x0, y0. So now we know that when we go distance delta x, we shall get to the value of y, which is y1, and that value of y1 is y0 plus delta x times this. Now we can go to the next point. So we write y2 minus y1 over x2 minus x1, which is delta x, and that's equal to f. But this f is between x1, x2, and so this is x1, y1. We know y1 because we've found it up above, and so we've found y2, which is y1 plus delta x, f of x1, y1, and so forth. Now we can find y3, y4, etc. Of course, the smaller you make delta x, the more accurate this will be. Clearly, the smaller that you make delta x, the closer you're going to get to an exact solution of this equation. Let's solve a differential equation approximately to make this procedure clearer. So let's take this differential equation. Dy by dx is xy squared plus 3x. And now that's a fairly complicated differential equation for a beginner, but it has an exact solution. We'll see that later as well. We need an initial condition. Let's take that to be y at x equals 1 equal to 2. To solve this approximately, we'll need a grid spacing. Let's take that delta x to be 0.03, in which case our first point will be x0 equals 1. The next one will be x1 equals 1.03. The one after that will be 1.06, etc. At x0 equal to 1, y0 is 2. When x1 is 1.03, we need to find out what y1 is, similarly y2, etc. Now y1 is y0 is 2, plus delta x, which is 0.03, times f, this is f of xy, and we'll evaluate this at x equal to x0, y equal to y0. And so that's 1 times 2 squared plus 3 times 1. And this over here is 2. And this over here is 0.21. So this is 2.21. We therefore have the coordinates of the first point after the initial point. Next, now that we know y1, we can find y2. So y2 is y1, which is 2.21, plus this increment. And now here we're going to take 1.03 times 2.21 squared plus 3 times 1.03. And that works out to 2.45. So this over here is 2.45. And similarly at x3, I can get y3 and so forth. Now let's plot these points on this graph paper. So here is the first point. That's x0 equals 1, y0 equals 2. Next point, next, 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 next. And now I'm going to compare this against the exact solution. Initially, you can see that we were doing fairly well. So here, 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 it wasn't bad, but it started becoming bad as x increased. And by the time we reached this last point over here, things were getting fairly bad. And if we go still further, it'll get much worse. That's telling us that this solution is not accurate enough. Well, maybe we could make delta x smaller over here, but then how small can you make it? Ultimately, you're going to reach a situation where the accuracy is going to fail. And that's why we need exact solutions if we can get them. You might have got the impression that all differential equations are difficult to solve, but that's not true. This equation is very easy to solve, and that's because we have made this particular choice of capital F of x and y. This is just a function of x, not a function of y. In fact, you can write down the solution immediately. So it's the integral of f all the way up till x. The lower limit we'll talk about later. It'll just result in a constant which can be fixed by the initial conditions. Now, this is actually obvious because we had defined the integral as the antiderivative. Or if you want to look at it in a different way, let's remember that the definition of dy by dx is you evaluate y at a slightly different value of x. So let's make that from a to x plus a slightly different value, delta x. So that's ds f of s, and then minus the original value, which is all the way up till x of f of s, divided by delta x. Now here I'm going to exchange a with x. So I'm going to call this a and this x, but then I'll have to change the sign here. This becomes a plus. Here we have now an integral x to a and then a to x plus delta x. We know from our study of integrals that that then is just this integral, and now as delta x gets smaller and smaller, this interval becomes smaller and smaller, which means f of s then is very close to f of x, so we can take it outside. And the integral of 1 between x and x plus delta x is delta x. And at the bottom we have delta x. We can just cancel this. So that's a quick proof that dy by dx is f of x and is a solution of this differential equation. Now let's solve this example. dy by dx is equal to x plus sine x. Y of 0 is 1. So looking at the formula above, all we do is we integrate s plus sine s, and we integrate it up till x. Never mind what's over here, we'll fix that soon. And this is equal to half x squared minus cosine of x. And you can see that if you differentiate this, you get x. If you differentiate cosine of x, you get minus sine of x, and so that becomes plus. But there's also a constant over here that we could add, because a constant differentiated gives you 0. Now the requirement is that when x is equal to 0, y is equal to 1, and so obviously c must be equal to 2. And so this is the solution of this differential equation with this initial condition. Here we are asked to solve dy by dx equals f of x, where f of x is this function here. Let's sketch that function f of x first. So here's f of x. It's 0 if x is less than or equal to 1. So here is the point x equals 1, and it's equal to 3. So here is 3 if x is greater than 1. We're also told that y at minus infinity is minus 1. So here is the solution. Y of x then has to be obviously minus 1 if x is less than or equal to 1. And now dy by dx has to be the integral of 3 if x is greater than 1. So if we integrate, we get 3x plus a constant c. Now if we require that y of x be continuous at x equal to 1, then we must have minus 1 equal to 3 plus c, which means c is equal to minus 4. So the solution, when all is said and done, is minus 1 for values of x less than or equal to 1, and it is 3x minus 4 if x is greater than 1. You see that at x equal to 1, y is minus 1 coming in from the left, and y of x is minus 1 also coming in from the right. So here is what the function looks like. So here it is minus 1 all the way here, and then it starts increasing with slope 3, and that is then the solution of this differential equation with this initial condition. There's another type of differential equation which is also fairly easy to solve, and that is this type. dy by dx is a function of x and y, so also of y, but where f of xy can be written as a product of a function of x and a function of y. In other words, it can be separated, and so this is an example of a separable first order differential equation. Many different possibilities exist for g of x and h of y. So g of x can be, let's say, 3x squared plus square root of x plus sine of x, etc. h of y can be, let's say, sine of e to the y. Of course, that's very, very difficult. It would make for a very difficult equation. But the point is that h will depend only upon y, g will depend only upon x. Here's how you would solve this. Let's write dy by dx as g of x, h of y, and then write this as dy over h of y equals g of x dx. And now let's integrate both sides. So integrate this and integrate this. Integrate this all the way up till y. Integrate this up till x. Don't worry about where we start this integral or this integral, because that will be absorbed into a constant, and that constant we shall determine from initial conditions. Now, if this integral is something that you can do, and this integral is something that you can do, then this equation can be solved. Let's work out an example. Here's an example of a separable equation. So we have dy by dx equal to, let's say, 2x into y squared with some initial condition y of 1 equals minus 2. So when x is equal to 1, y is equal to minus 2. This is called separable because this factor over here of 2x depends just upon x, and this y squared depends just upon y. So it's been separated into a function of x and a function of y. Let's write this as dy over y squared equals 2x dx. And now I can integrate both sides. I can integrate this and this. When I integrate this, I get minus 1 over y plus a constant equals x squared plus a constant, and I'm going to combine both into the same constant c. Now, when x is equal to 1, y is equal to minus 2, so we have half is equal to 1 plus c, and from here c is equal to minus a half. Therefore, we can write our solution y as minus 1 over x squared minus a half. And now that's the solution to our equation over here. It also has the correct initial value. When you put x equal to 1, you get y equal to minus 2. But now you see, there is a problem whenever x squared gets close to half. In other words, when x is either plus 1 over square root of 2, or when x is equal to minus 1 over square root of 2, there is now a division by 0. And that's telling us that there is a range of validity. So the range in which this solution is correct will be between 1 over square root 2 and minus 1 over square root of 2. In this range of x, this will be the correct solution, but not outside of it. Here is y plotted against x. Here is x equals 0, and at this point y is 2. Now you see that as you approach this limit over here, 1 over square root 2, or as you approach this, minus 1 over square root of 2, that the function goes to infinity. And so within minus 1 over square root 2 and plus 1 over square root of 2, this is indeed the correct solution, but not outside of it. Let's take another example. Here is dy by dx equal to minus 3x over sine of y. Now this is separable because 3x is just a function of x and it's multiplying 1 over sine y, which is a function of y only. There's also an initial condition that y of 0 has to be pi by 4. And now let's cross multiply. So sine of y dy becomes minus 3x dx. And now let's integrate both sides. So integrate from somewhere up till y and somewhere up till x. And when we integrate, we'll get minus cosine of y equals minus 3 over 2 x squared plus a constant or minus a constant, doesn't matter, it's the same thing. And so from here, we can determine the constant c. When x is equal to 0, we'll have cosine of pi by 4 equal to the constant c, and cosine of pi by 4, we all know, is 1 over square root of 2. So c is 1 over square root of 2, and so we can write our equation as cosine of y is equal to 3 over 2 x squared plus 1 over square root of 2. And so the solution is y equals cosine inverse of 3 over 2 x squared plus 1 over square root of 2. And now, although this is the correct answer, is this true for all values of x? Obviously not, because let's say that x becomes very large, then this over here will become bigger than 1, but cosine of y has to be less than 1. So let's use the requirement that cosine of y has to be lesser than or equal to 1, which means that 3 over 2 x squared plus 1 over square root of 2 then has to be lesser than or equal to 1, which says that x squared has to be lesser than or equal to 2 over 3 into 1 minus 1 over square root of 2. And so that says that this over here is a solution provided x squared is less than this, which of course means that x has to be lesser than or equal to the square root of 2 over 3 into 1 minus 1 over square root of 2, and it has to be greater than or equal to minus that same number. So 2 over 3 into 1 minus 1 over square root of 2. So provided that x lies within this range over here, this will be the correct solution. But now let's plot this solution and see what it is. Here is the plot. This number square root of 2 over 3 into 1 minus 1 over square root of 2 is this number over here, and minus that is obviously over here. And so this range of validity goes from here all the way up till here. At this point, at this very end point, cosine of y is 1, and therefore sine of y is 0. And so you can see that dy by dx will then be 1 over 0, or some number over 0, and that's infinity. And that's exactly what you see over here, that the derivative goes to infinity here, and of course over here. On the other hand, when x is equal to 0 in this solution or over here, then cosine of y is 1 over square root of 2, which means y is equal to pi over 4, and pi over 4 is this number here. So we have checked that this is indeed the correct solution and has been plotted correctly as well. Finally, we want to solve the motion of a parachute as it descends downwards. So here is the equation that we had written down before. Mass into acceleration is the total force, so that's the weight acting downwards, minus the air resistance, which is assumed to go as the square of the speed, and V0 is the speed at time t equals 0 when the parachuter left the plane. Now, since we are interested in just solving the equation and not in a real problem, let me just put m equal to 1, g equal to 1, k equal to 4, and that'll get rid of a lot of constants over here. But I'm going to leave V0 as it is because I want to show that the final velocity does not depend upon V0. So this equation then becomes dv by dt is 1 minus 4v squared. And that's what we want to solve. Now, one thing before we solve this in full detail is to note the following. Suppose that the velocity stops changing with time. So I'm saying if and when the velocity stops changing with time, then we'll have to have 1 minus 4v squared equal to 0, which means that v will have to be half. It can't be minus half because this is speed. So when the speed stops changing with time, then that speed will have to be half, and that's called the terminal velocity or terminal speed, if you like. And notice that it doesn't matter what v0 is. So how are we to understand this fact in detail? Let's then solve this equation here. So let me start by writing the equation. dv by dt is 1 minus 4v squared. Now from here, I can get dv over 1 minus 4v squared equals dt. So this is, after all, a separable equation. This is just like a function of y. Well, that y is the v over here. And now let me integrate both sides. So I integrate this and I integrate that. So now what we have to do is work out the integrals. Now 1 over 4 minus v squared is 1 minus 2v into 1 plus 2v, and this has to equal integral dt. But now what I'm going to do is split this up in the following way. I'm going to write this as 1 over 1 plus 2v plus 1 over 1 minus 2v. And so if I add them, I'm going to get on top 1 minus 2v plus 1 plus 2v. So I've got to divide by half. And that is integral dt. Now, we can easily integrate this. This becomes half, and this becomes log of 1 plus 2v, but we've got to divide this by half. And then from here, the only difference will be a minus sign, and here I'm going to get log of 1 minus 2v, and that's equal to t plus a constant. We're going to determine that constant from the initial condition. Well, let me write this now as log of 1 plus 2v over 1 minus 2v. That's because log of a minus log of b is log of a over b. There's 1/4 out here. I've taken both the halves out, and this is equal to t plus c. So now I can write 1 plus 2v over 1 minus 2v as the exponential of this. And so 1 plus 2v over 1 minus 2v is e to the 4t e to the 4c. Now e to the 4c is another constant, so just let me call that a. And of course a is determined by the fact that when t is equal to 0, the velocity is going to be v naught. And so that tells us that a is then 1 plus 2v naught divided by 1 minus 2v naught. v naught being the initial speed, the speed at t equal to 0. Okay, so now I've run out of space. Let me go here. And now you see that I have the solution, because I can write 1 plus 2v equals e to the power 4t into a times 1 minus 2v. And then I bring the v on this side, so I'll get v into e to the 4t into a minus 1 equals e to the 4ta, or rather there's plus 1 over here and there's minus 1 over here. And so finally I get v is, and there's a 2 over here that I missed, so I get v is half of e to the 4t a minus 1 divided by e to the 4t into a plus 1. And that is the final answer, where a is given over here. Now, let's see what this is telling us. For t equal to 0, you can see that I have a minus 1 over a plus 1, and there's a half outside, and that becomes v naught itself. A second point, and this is the more important point, that as t becomes larger and larger, e to the 4t times a becomes much, much larger than 1, and similarly downstairs over here as well. And so forget about the 1, so this and this cancel, and so v will go to half as t becomes larger and larger. Now, here is the plot. So you see that the velocity increases as time goes on, and it levels off at v equal to a half. So in the limit as t goes to infinity, you have v of t tending to a half. Now, does it matter what the value of v naught was? The answer is no. It could have been bigger than half, or it could have been less than half. In either case, that would have affected only the value of a, and a is down over here, but a cancels out. So the point is that you reach this terminal velocity. That's in the nature of this equation. And the reason for that is that as v stops changing with t, v will have to approach 1/2. We did see some interesting examples of differential equations in this lecture and saw how they come about in certain physical systems. But we still don't have all the tools that are necessary to solve every first-order differential equation. This we shall concentrate upon in the next lecture.